Hello, this video is about databases and SQL queries on a free and open source tool called PG Modeler, which is an entity relationship diagram software for the famous and free database PostgreSQL. The talk is mostly about the recent development that I made of a sql-join path solver. The feature can be mostly useful to get to extract rapidly sound information from a database, and as it is helping me right now to reverse engineer an existing model. To try and give a broader view on the topic, this can be considered as a small part of NLIDB, which is Natural Language Interface for Databases. This is a research area that went live in the 60s. Well, it has done no famous achievement yet, mostly because the problem of mapping the natural language question semantics to the existing data model is very far from trivial. NLIDB consists of a few building blocks, which are each quite entire topics in themselves. The first up front is natural language processing, sometimes preceded by speech-to-text processing, which converts plain English into an intermediate representation, and then feeds into the core engine, which is roughly both keyword mapping that selects the tables involved, and path inference, which selects from the tables deduced relations and join between them. There are usually post-treatment after that, which leads to SQL execution. Many white papers also use other fields like the relation semantics. Think about Tim Berners-Lee long-awaited Web 3.0, and very structured things like ontologies, RDF, and the language SparkQL. Some others use SQL logs to produce better results. And of course, there have been attempts in 2019 at machine learning and deep learning on that topic. I'll provide links in the video description on those white papers if you're interested. For now, we will restrict to a much simpler part of the problem and quite put away the problem of relation semantics and work around that with sheer edge weights, which can mimic the semantics somehow, and produce a ranking of path weights, and from that let the user decide which path is best for him and which semantic it represents. The keyword mapping feature in PG Modeler is quite already there with the object finder feature, and we focus here on the second part of the core engine, which is path inference. The input of the feature is a given set of tables you want to join, and you will get as a result candidate paths ranked We'll get to that in a minute. But first, some maybe notions about graphs. The graph is already with PG Modeler and our topic quite ready to go. The tables are vertices. Foreign key relationships represent edges. And we add to that weights on edges, which can be parameterized at will. We'll see also that. This is not a crash course about graph theory. I highly encourage you to discover that topic if you don't know about it. It's much fascinating. You probably know already of the most famous, which is the traveling salesman problem. There are lots and tons of others. Here we mainly used 3 main algorithms. When we want to join only 2 tables, this is considered a very simple problem in graph theory, and this is the 2 points shortest path problem, and use things like Dijkstra, path planning algorithm like A-star. Here we will use Dijkstra as we get to it. In the second case, if we want to join 3 or more tables, we get to another type of problem, which is the Steiner tree problem. This is a generalization of the minimum spanning tree problem, and is a hard problem. It's actually NP complete. If you want the best introduction about computational complexity on the internet, I'll give you a link in the description or somewhere. And let's get to our implementation. Currently it consists of 3 main steps. The first one simply detects tables that can be reached by relations from the root table. This is called in graph field connected components, and uses a custom depth first search. The second path is, depending on if you want to join 2 or more tables, simply shortest path for 2 tables, or for 3 or more, a combination, actually a multiplication of Steiner trees and shortest path. I put k plus 1, which is a refinement of those algorithms that produce rankings, not only the best, but all the best, and more. Some that have a good score, but not the best. The amount of which can be parameterized. The algorithms here are that I use have been written in the PAL library, which is an open source lib on top of the BoostGraph library. That's for the main part, which the second part, which detects candidate paths. And lastly, as is done with the manual mode that we talked in earlier videos, there's a topological sort round, which is done with yet another custom depth first search to just order the relations and produce the SQL. That's it for the theoretic part, and let's move to some examples. We'll start with very simple 2 tables to join shortest path problems. Here we have an illustration of the k plus 1 shortest path. If we want to join tables 0 and 1, it's quite straightforward. There are 3 paths. The direct path, which cost is 1, that is with a default edge weight of 1. The second path gets 2 relationships involved, and the third, the 3 above. here you have the tables involved that are not part of the set of tables you want to join. As I showed you, you can shift click on the path and it will highlight the relations. To move to a somewhat more complicated example of shortest paths, here is what I've been told in my database courses that should never happen. Transitive closures which are bad, but in practice, and as I've seen, they are everywhere because of denormalization, because the model needs this. So here we have two cycles. If we want to join table, say 1 and 6, it's pretty easy for you to figure that there are 4 paths that can be used. If we use the default age weights, all 4 paths have the same cost, and we see them here. The 4 candidate paths. We can also, as I was talking about mimicking the semantics with weights, put in parameter here a custom weight. For example, if we want to say that traversing one table has a higher cost, or we don't want to see results associated with such a table, for example 3, we can say that on the relation 3 we want to add an extra cost. This will be taken as input in the graph, and now if we run again the algorithm, the minimum cost of 4 stay away from table 3. Well, that's it for this example and shortest paths, which remain very simple. The most often used queries, 2 tables to join. In the case we want to join 3 or more tables, we get to such an example. Let's say we want to join table 1, 2 and 4. There will be a Steiner path problem solved, and underlined here is the Steiner point. That is a central point that is used to shorten the cost of the path. So 0 is a central point here in our query, and from 0 we draw paths to the input tables, which we call terminals, and we get the result of a Steiner tree problem. Very simple. Now if we move to a bit more complicated Steiner tree problem, another transitive closure, you can figure out quite easily here that if we want to join those 4 tables with a minimum cost, there are here in this square 4 ways to get a minimum cost result, which is a U shape in the 4 directions. Let's see. We get U shapes, 4 U shapes. Well, nothing much to say about it. The Steiner trees, the Steiner points are 1, 2, 1, 3, 2, 0, 3, 0, a combination of the 2 among 4 possible here. And now if we mix the Steiner tree problem with shortest paths, multiple shortest path problem, and the previous examples, we can get such a model. If we want to query the 4 limit tables, and join them together. Here we will get a multiplication of the, let's run it, we get 16 results, which is a multiplication of the 4 paths we saw before for the U-shape and the 4 paths here for the short espace problem from here to here. All of those paths here have a cost of 17, and they are by U-shape. 1, 2 here, 4 results for the 4 short espace here. Well, we get the multiplication of the 2 problems results. So 4 results for the Steiner elements 1, 2, 4 results for the Steiner elements 1, 3, and so on. That's it for the simple examples, and let's move away from sketches, from mockups, and move to a real-world application. I'll show you the model I'm working on currently. It is a fairly large model with 1500 tables and around 2K relationships. This is a warehouse software model, so it talks about receipt numbers, picking numbers, goods, locations in the warehouse, and to quite illustrate what keyword mapping is, using the object finder feature. If we want to say search for receipt numbers, so yeah, here I found my table receipt. I select it, and then that's the query, the keyword mapping example. I insert it directly in my query. If I want to join, let's say, a picking, well, I know by heart those tables, can insert it with a few other to illustrate. That's the good table, the main goods table, and the location, or the item, one of the item tables. Now if I go to parameters and lower a bit the outputs of the algorithms to not get too much time complexity, I can do that here. And if I want to add another age weight, here in my model I have something that the software company called work tables, which is quite an ugly thing. That is temporary tables that hold nothing but the transient information and persistently stores nothing. I can add an extra cost on table with name of with the pattern that those working tables use, and then an extra cost, so they will not be displayed in the result. Now if I run the query, I will get an output a few candidate paths. And as this is in French, I will go in further detail about this example and the query results in another video in French, I think. So stay tuned. One thing we can notice is that even with a fairly large model, the performance is really good, which is cool. And yet, in the algorithms and the implementation, there is an awful lot left for optimization. But yet the performance is here. That's mostly it about this video. I wanted to talk about limitations. For now, parallel edges are not supported. They will in a close future. Another limitation is that the time complexity is pretty high. The optimal Steiner tree problem solving has already an exponential time complexity, and the custom k+1 Steiner tree I made around it as a black box also add exponential combinatorial searching, so that's not really clean. If you want to add here, for example, 2 or 3 more tables, it will take a lot time. It can be quite intractable, but well, such cases where you want to join more than 5, 6, 7 tables are quite rare. Lastly, I'm in the process of stripping or re-implementing the algorithms to, instead of having and adding a heavy external dependency like Boost to the PG modeler project. And that's it for today. I hope you enjoyed it, and any feedback is very welcome. Thanks. See you next time.